Finally I can see the island again. Oh, there's some noises there. Good thing I have some equipment. That's a bit too many. Maybe I just walk past them. I just want to sleep. Also, I haven't slept in days. I don't know what's going on. What even is this? Oh no. Oh. Okay. I starved to death? What? As you might have guessed from the title, this is not actually a survival video. This is another shader tutorial, so welcome back. And the topic for today is how to implement a post effect just like this one. So you can see here on the border you have all these tentacles wiggling around, you have the eyes opening and closing, you have all the borders on screen also wiggling around, and you have all the colors being desaturated. And everything is stuff you can relatively easily do inside a post-processing shader, the same kind that I explained last time how to do in Minecraft. But what I didn't explain is how to basically live out your own artistic vision. Like you have all of this creative stuff going on here, but I just said this is a mathematical function and didn't explain any further. And it's true that all of these tentacles, for example, this border on the screen and the opening and closing animation, all of this is just a mathematical function, but well, how to actually write it out inside a shader file, this isn't entirely obvious without being explained, so this is the topic of this video. We will start our journey on shadertoy.com. This is a website where you can create your own shaders and share them with other people, and I often use it for prototyping post effects for the simple reason that the format of these shaders that you write on Shadertoy are pretty much the same as what you write inside a Minecraft post shader. So for example, this would be an empty shader inside Minecraft, and you can see you have this input that just gives the current texture coordinate and an output that just lets you write to the screen. And you have this main function that just runs one time for every pixel on the screen. And you have the exact same thing on Shadertoy, like you have this main function, an input that gives you the current pixel coordinate, and an output that lets you write to the screen color. And well, in Shadertoy, when you press this new button, you get this color gradient. Let me just replace that with black. And update using Alt-Enter. And this is basically the main reason for why I write inside Shadertoy instead of Minecraft. Basically, I can instantly update any changes that I make, like let's make it white instead. And I can just press one button instead of needing to reload my resource pack in Minecraft. So inside Shadertoy, you have this exact same format, and let's start writing the effect. The basic shape that I want to start from to make the effect is this triangle shape that the tentacles have, and it doesn't need to be anything complicated, just a basic triangle. And a triangle has three sides, and two of the three sides are actually already done by default because our screen already has edges. So the only thing that I actually need is a diagonal going across the screen. So maybe let's first visualize the screen coordinates. And I just want a diagonal going from here to here. And a very simple way to do that is just by doing uv.x plus uv.y. And there we have a diagonal. The way this works isn't really complicated. Just when you add x and y, it goes diagonally from bottom left to top right. And when you move perpendicular to that, you have a constant value. And this is where this line comes from. And to make this line even sharper, like right now it's basically a linear gradient from the corner to the center of the screen. To make this more sharp, we can use something called the smooth step function. 0.991 maybe. Okay. And this smooth step function just basically takes this third argument that we had as the input and asks the question, where is this input smaller than the lower bound, or where is it larger than the upper bound? And anywhere outside it's just either completely black or completely white, and anywhere in between these two bounds it blurs. So for example, when I make these bounds farther apart, you can see that there's a blur between 0.9 and 1.0. And well, I can also show this smooth step function inside Grayscale. Grayscale was made by the same creator as Shadertoy. It's just a neat way to visualize the function that you have inside Shadertoy. So for example, 0.9 and 1.0 and x. And here you can see anything below 0.9 becomes 0 and anything above becomes 1. And in between we have this cubic interpolation. You can also see the interpolation way better when you interpolate between 0 and 1. So you can see the slope at the start is 0, the slope at the end is 0, and in between it's smoothly interpolated. And here we have this triangle that we wanted, but to make it look more symmetrical, because it's way better to work with symmetrical shapes, I want to move this triangle to the right by half a unit and then mirror it to the left. So moving it to the right isn't all that hard. You just have to write uv.x minus equals 0.5, and it's been moved successfully. And to mirror it, I can just write uv.x equals the absolute value of uv.x. Okay, and now it's the same on both sides. The simple reason for why this works is just when I go back to outputting the UV coordinates. Originally, when I subtracted 0.5, it was 0 in the middle and it went into the negatives on the left side. Taking the absolute value just makes it go in the positives, so on the left side it's displaying the exact same thing as on the right side. So now we have this mirror triangle, and maybe we want it to be more steep. And because this is a mathematical function, I can just increase the slope by multiplying the function by 2. So uv.x times equals 2, and now the slope is 2. So now we have this basic triangle shape, and the next step might be to make it wiggle around, like make this line look like a sine wave. Like we have here in the shader, it kind of looks like a wave. So maybe we can write uv.x plus equals sine of uv.y. Okay, this is a bit intense. Maybe let's do 0.5 times the same thing. Okay, now it's looking a bit wavy. Well, but sine isn't very interesting in that short range. Maybe let's do it a bit more intense. Maybe let's do it times 0.2. Yeah, that's way better. And another thing that I don't like is how it just looks like a still image. I want the wave to move around. So maybe let's just shift the progress of this wave by the time. So for this I can just write minus I time. Okay, and now it's moving upwards. And you might wonder where this I time comes from. This is just a Shadertoy specific thing. Like here you can see the shader inputs, and I time is just the playback time in seconds. So now we have this waving effect, but actually something I don't like is how the bottom of the tentacle moves exactly the same amount as the top, because, well, you could imagine the tentacle is attached to some living creature, and the bottom, of course, isn't moving. The creature is just wiggling the top of the tentacle around. So I would want to multiply by a value that is 0 at the bottom and 1 at the top, and this is very easily uv.y. Yeah, uv.y is just 0 at the bottom, so it doesn't move at all at the bottom, and it moves the same amount as before at the top. And this wiggling looks pretty nice. I'm pretty happy with it. So let's move it into its own function. Maybe call the function tentacle, so vec3 call equals tentacle of uv, and we have to actually create the function, so vec3 tentacle of uv and add a return value. Okay, and nothing changed, so we didn't do anything wrong. And now we can move on to the next step, and that is adding more than one tentacle. When you look inside Minecraft, you can see that I have these 10 different tentacles all around the screen. And for now, we don't yet wrap them around the screen, but maybe just let's display them side by side. So that a different x coordinate basically means having a different tentacle. And for this, the basic idea that we don't exactly repeat the tentacles, but instead we repeat the UV coordinates. So let's go back to displaying them. And we want this red gradient to repeat a bunch of times along the x-axis. And there's a pretty simple way to do that. For this, I will go back into the Grayscale editor and show you what the fract function looks like. So the fract of x looks like this, and as you can see, it's repeating. The basic idea of the fract function is just that it removes the integer part of a number. So the counterpart of fract would be the floor function, like this. And the floor just rounds down any number. And using the floor function, you can also come up with your own definition of fract, and that would just be x minus floor of x. Like this. And you can see it looks exactly like the fract function. And it has this repeating pattern that we want. So let's just write uv.x times equals 10. So that we actually have space for the repetition, and uv.x equals fract of uv.x. Alright, and now it's repeating exactly like you want, and we can go back to inputting the uv coordinates into the tentacle function. So tentacle of uv, okay, and we have 10 different tentacles. Very nice. At this point we can also make the wave pattern a bit stronger, so instead of multiplying our UV by 10, maybe let's multiply it by 20 and make the amplitude also a bit stronger. Okay, so with this we can see the waviness a bit more, but we also notice that the wave pattern looks exactly the same for every tentacle and that they look completely in sync, and we don't actually want this. So what we need here is a way to basically have a different wave pattern for every tentacle, and then we can enter the number into our wave pattern, and this lets us mix up what these waves look like. So let's maybe copy all of this back into the tentacle function so that we have access to the original UV. And as we saw just now, the floor function is exactly the complement of the fract function. So when we just take the floor of the UV, so floats id equals floor of uv.x, we just get inside this id variable the number that is different for each of these different sections. So when I go here and add this id as a different parameter to the output color, so maybe id times 0.5 and 0 as the third argument, you can see that the ID just changes for every cell that the different tentacles are in. So when I add the ID inside the assign function, you can see that every tentacle is shifted by some different amount. I can also multiply this by some value to make it look a bit stronger, so maybe times 2.35. Yeah. Now all the different tentacles look quite different. Maybe this looks a bit too close to being mirrored. 2.2, yeah, I don't know. But I do think it looks a lot better than it did before. So when I go back to not showing the cells, yeah, now the different tentacles don't look like they're completely in sync anymore. So I can write, I can also make the time a bit faster because I don't like how it looks right now. So 1.5 times I time. Or maybe something even more extreme, 4 times time. Yeah, now it's moving around quite a bunch. Actually, I liked how it looked before, so 2 times time, okay. But now, what I'm really missing is for the tentacles to move in from the outside instead of just coming from the bottom. So when you look inside Minecraft, you can get an idea for this. All the tentacles are on the outside, and they're basically moving inwards, while on the in our shader the tentacles are just lined up side to side and are moving upwards. And the way to fix this is by using something called polar coordinates, and maybe let me just write it up and explain what it does. Okay, so this already looks quite cursed, but you can see the tentacles are lined up side to side, or not anymore. Instead they are lined up along the angle, and they are all moving outwards. And I don't actually like that they are moving outwards, because I want them to instead move inwards. This also isn't that difficult to fix. I just have to basically write uv.y equals 1 minus uv.y. Okay, and now they're moving from the outside to the inside. And maybe make them not move that much to the inside, because it looks very distorted so close in, and I don't want it to be there anyways. Yeah, now they are only on the borders, or maybe 1.5. Okay. And the next thing I'm noticing is that it's all centered on the bottom left of the screen. This makes sense because that's where 0 is, and the polar coordinates are centered around 0. And let's first do just uv minus equals vec2 of 0.5. Okay. And maybe move the tentacles a bit more inwards. Yeah, right. But now it's finally time for me to explain what these polar coordinates actually do. And the idea is that they don't represent a point as a Cartesian coordinate pair, like using x and y, but instead as an angle and a distance from the origin. So when you draw up a picture, in x and y we have our traditional Cartesian coordinate system, but instead we can also represent the same point in space using this angle alpha and radius r. And this is basically exactly the conversion that we do right here. Like we have this length, that's just the radius, and we also have this angle alpha. And basically when you take y over x, this is the definition of the tangent of alpha, because this is a right-angled triangle. So when you take the arctan of y over x, you get back the angle alpha. And this is basically what I'm doing here, except instead of dividing y by x, GRSL has this special version of atan where it basically fixes the problem that taking the opposite angle, like 100 degrees offset, would give the same fraction. So this special version just has you give the y and x coordinates separately, and then it figures out the angle on its own. And when you plot it, it looks like this. Here you can see that, well, in green we already changed the distance a bunch when we move it. Yeah, it's 0 in the center and then just becomes more green when you go outside. But also on the red channel we can see that the angle is 0 on the right and then goes to 1 over here, and then it basically goes up to pi here on the left side, and when you go on the opposite side it goes up to minus pi. We don't actually want this. Instead we wanted to go from 0 over here to 1 over here. So let's fix that. uv.x from minus pi and pi to 0 and 1. uv.x equals uv.x divided by pi. Now it's in the range from minus 1 to 1, and times 0.5 plus 0.5 now brings it to the range from 0 to 1. And the shader doesn't actually know what pi is, so let's teach it. Define pi 3.14159. Okay, and now it's way more nice. And when we go back to displaying our tentacles, yeah, now it's back to displaying our 10 tentacles instead of like 60. Okay. We can do some further adjustments to what our tentacles look like. For example, I don't like how intense they are. I want the amplitude to be a lot less. Very well. And this already has the whole polar coordinates conversion finished. The next thing that I don't like is how predictable the tentacle motions look. Like when you look at it for a second, you can see that it's basically just the same shape moving to the inside, and it doesn't look like a creature is actually moving it around. When you look back inside Minecraft, you can see that it's not very predictable. It's basically just the tentacle doing its very own thing. And so what we are missing here is basically a tentacle motion that is not just a sine wave, but instead controlled by some random numbers. And random numbers in shaders aren't all that easy to do. You have to define your own random functions. For this, people have already made their own approaches. This is one of them. It's a Shadertoy called hash without sign. And when you switch to this common tab, you see all of these different hash function is what it's called. And these functions just have some input and some output. And the idea is that for every input, the output is always the same because it's still just a mathematical function. But instead, when you change the input, the output just becomes a completely new number. For this, they are basically just throwing together a whole bunch of random nonsense. They're also described in the comments that they just chose some random numbers until it looked right. But I do think it does look very right. It looks like very nice noise. And so that's what we're going to use for this. And in our case, what we need is a three-dimensional hash function for the simple reason that when you count all the inputs that we're using for a sine function, we have uv.y, we have itime, and we have id. We need three different numbers. So what we copy is this hash13 function that just has vec3 input and float output. So let's copy this into our code. And just for fun, let's try using this instead of the sine function. And as you can see, our whole code is completely screwed up. And this makes complete sense because we want all the different waviness to be continuous between different pixels, but our hash function is completely discontinuous. Like when you look at it like this, all the pixels are completely different colors. A naive way to make it continuous is to just round down our inputs value, so maybe do floor of this whole vector. And now it doesn't look noisy anymore, but you can see all these different cuts between the values. And to get a better understanding of how this cut works and how to fix it, let's switch into our Grayscale, because this Grayscale also has a cell noise function. And this is basically the same thing that we have right here. Like we have a hash of a floor, and so it returns a new random number for every section. So the way to make this function continuous is basically to add a copy of this function, except that it's shifted by 1, like this. And the special feature of this copy is that it's continuous with the next copy of itself. So when you go to any point and basically interpolate between the bottom and the top value by how far you are along this line, you just get a line segment that is pointing from here to here, and so all the line segments end up being continuous with each other. So when I write it like this, mix of f1 of x and f2 of x, and mix it across this progress, so the fract of x, right? We get all of these line segments. And this is something that we can already write inside our shader, except in the shader we don't have this one-dimensional function anymore, we have a two-dimensional function, because uv.y and itime both are continuous variables. id is just an integer, we don't actually need to interpolate along that. So what we do is we write float noise vec3p and just write the logic that we had just now, but with 2D instead of 1D. So instead of taking 2 different points, we take 2 by 2, so 4 different points. So what we have is float r1 equals hash 13 of p, or actually not p, because this cell noise is a hash of the rounded down x. So what we need is vec3 fl. Fl is just the floor of p. Okay. And now we can take the hash of fl and take the hash of fl plus 1, or in our case not 1, but just a vector that is shifted 1 in towards the y direction, and also call these different numbers. And now we can interpolate between them. For this we again need the fractional part. This time we just need a vec2 because we just need to interpolate across x and y. And return the interpolated value. Here we use fr.y for the simple reason that the difference between r1 and r2 is just that we add 1 across y, and repeat the same thing except between r3 and r4. And we can mix between these two values using fr.x, because the difference between these two and these two is just that we add this 1 across x. And when we use this inside our function, yeah, it all looks continuous now. Except the issue that we have now is for the human eye, it's very easy to see when the direction of something changes suddenly. This is true both along this uv.y axis and along the time axis, so this is very noticeable. And a simple way to change that is by basically replacing these line segments with cubic functions that have a slope of 0 at the start and end. So when you stitch together these cubic functions, they all look like they have a continuous slope, because the slope is just 0 at the start and end, and 0 matches with 0. And we already know a cubic function that does exactly that, and that is the smooth step function. It looks like this. And now it looks very smooth, as the name says. This is also easy to add inside our shader. And now our tentacles look smooth too. But we are running into a new issue, and that is that it's very noticeable that the slope just becomes 0 every second. So this doesn't exactly work. And we also see inside our graph, like it becomes 0 here and here, but in the end result it becomes very noticeable when it basically stops moving every second. So yeah, it looks like a very predictable wave, and we don't want that. The way to change that, to make the slope not equal to 0 at the start and end, is to basically change our base functions that we interpolate between. Because at the moment these are just constant functions within each segment, but the only thing we need about them is just that we have some dark yellow function, and we need the light yellow function to match up with whatever slope and value the dark yellow function has at the next interval. So one choice for this is to just make the dark orange function a linear function that just starts at 0 and has some random slope. So we use the cell noise not as the constant value, but as the slope of the function. And we could try writing x times this whole thing, but this goes horribly wrong when we go to different regions. Instead we want the fractional value of x. Okay, Yeah, and now we have these random slopes. And for f2, we basically need to set it to exactly the function such that f2 in this cell matches up with f1 in the next cell. So for this we can write fract of x minus 1 times the cell noise of the next cell. The basic idea for why you write minus 1 is so that it reaches 0 at the next cell and it doesn't start at 0 in this cell. And now that we have these two functions and they match up with each other, we can again interpolate between the two in each cell. And we get this new smooth function, and it has a random slope on each integer coordinate. So this is also something we can write in here, except now we can't just write a single slope. We have to write a slope across the x-axis and the y-axis. So let's maybe write a new function that returns a random value across x and y. Let's call it gradient, because gradient is just the mathematical term for a multidimensional derivative, like a slope across multiple directions. And a simple way to get two random numbers from just one is to just use this whole polar coordinate system again, except this time the other way around. So we just write float angle equals hash 1/3 of p and multiply it by 2 times pi. Now we can return the vec2 cosine of angle and sine of angle. If you know some trigonometry and look at this triangle, you can figure out the math for yourself. I'm not going to go into detail on it. But now a simple way to write this exact equation that I wrote right here, except for multiple dimensions, is just using the dot product. So when I write dot right here between fr in this case, so we have to write vec2 fr equals fract of p dot xy. Okay. The dot between fr and the gradient at fl. This is taking fr.x times gradient.x plus fr.y times gradient.y. So it's basically the 2D version of this whole thing. And we can repeat this whole idea for all the different points. Okay. And now it should already work. Nothing works. Right, I redefined fr right here. And it's complaining about the types. Right, fr is a vec2, so I can't just subtract a vec3. Yeah, and now it works. And it looks very random. I can't see any patterns anymore. Except now I think it's way too fast. Maybe let's multiply time by something other than 2. Yeah, 1 looks way better. And the amplitude could be a bit larger, so maybe times 0.2. No, that's too much. 0.15. Yeah, right. At this point I'm happy with how the tentacles look, but there are still some features left that I would like to add to this effect. For example, here in the game we can see this black border that I also want to add inside our Shadertoy. And this is a very simple effect. I already showed last video how to add it. Here we already have the length calculation for the distance from the center of the screen. So let's write it into its own variable. And maybe multiply this this value into our color. Okay, and now it's black in the center of the screen, but we actually want it on the borders, so let's write 0.6 minus ub.y. And now this black edge is exactly 0.6 units from the center of the screen away. And maybe to make this transition faster so that it's brighter in the center of the screen, multiply this whole value by 2.2 or something. Okay, and now it's not too dark anymore. Another problem is that the value is now larger than 1 here in the center and also less than 0 in the corner. So let's write max of 0 and this value so that it's always clamped to 0 from below, and also min of 1 and this value so that the same thing happens in the center and it doesn't get brighter than 1. One large part that is still missing from our shader is so that we can actually see what's on our screen instead of just seeing a white background. And inside Shadertoy we can do something like this by importing some textures. I like to use this London texture because it's basically the only preset texture inside Shadertoy that looks like it's from the first person. So let's write vec3 text color equals texture of I channel 0, and well, we messed up UV in a bunch of ways, so let's just copy it right here. UV equals this formula again, .rgb, and output this text color to our screen. Okay, now we can see London, and multiply this black tentacle color into our text color. Okay, and now we have both at once. And with this, there is something that we can see that we are missing in our Shadertoy that we had in Minecraft, and that is this domain distortion effect, where basically all the regular blocks look wiggly instead of just being straight texture lookup. And this actually isn't very complicated to do in our context, for the simple reason that we have this whole noise function set up. So you can just write here on the UV coordinates, we can just write UV plus equals noise of, I don't know, vec3 UV. Yeah, it's very extreme, but we can tone it down a whole bunch, like 0.001 might be enough. Maybe that's too small. Oh yeah, one more reason for why we don't see a whole bunch is because the frequency of our noise function isn't that large, so let's maybe multiply it by 20. Yeah, that looks way better. And now you can actually still see it. If we take a smaller amplitude, like this, you can still see some distortion. And when you enter the time as the third parameter, you can see it changing a bunch. But we still want it to look smooth, so maybe let's write this into its own value. So float R1 equals this, and then R2 is the same thing, but with time shifted by 1. And we can do the same trick of just interpolating between the two. So mix of R1 and R2, and fract of I time. Okay, now we should have this. Yeah, now it's wiggling around a bit. Maybe it could still do some more, so let's multiply this by 40 instead of 20. And make it a bit stronger again, so 0.4. Yeah, that's too strong. Okay, now you have this wiggle effect. So the last thing I want to add inside Shadertoy is just a desaturation effect. And for this we can simply take a grayscale of our color. This is very easy to calculate. Just write float grayscale equals the dot product of our text color, and vec3 that basically gives the weights of the different color channels. In this case I'm just setting all three to 1/3. So as I explained before, this dot product is the same as just multiplying the text color with the other vector that I write. and adding the results together. So in this case, it's just the exact average between the three. In actuality, you'd want to look up in Wikipedia, and it has a bunch of weights that you can actually use. Like when you scroll down, you can see here, you should write 0.2 for red, 0.7 for green, and 0.1 for blue. So maybe let's just write that. Okay. And now we can maybe try writing text color equals vec3 of grayscale. And we can see it's a grayscale image. And to get an image that looks a bit more desaturated but not but still has a bit of color, we can just mix between the grayscale version and the color version. So for example, 0.2 has it mostly desaturated, 0.8 would be mostly colorful, and you can of course write anything in between. Maybe 0.4 looks fine. And now we have this desaturated image, we have a black border on the screen, we have some screen distortions going on, and we have these tentacles on the border. And the only thing that I think is missing is these opening and closing eyes that you also have on top of this black border. And this is something I want to add inside Minecraft, because I want these eyes to be controllable via an actual texture that you can maybe ask an artist to make for you, or maybe you want to use your own pixel art skills. So the next step would be to take this whole Shadertoy demo and copy it inside Minecraft. And as you can see right here, I'm still on Minecraft 1.21.1, and this is for the simple reason that this original effect that I wrote is from several years ago. It's like from 2023 or something, and this shader tutorial is supposed to be for 26.3 at this point. So let me restart my game in the new version so I can port it over. So now I have my game restarted. You can see I'm in version 26.3, and I already set up my resource pack. So when I write /post effects add s, you can see I have my custom effects suggested. How to do this is something that I already showed in the last video, so if you want to do it for yourself, watch that one. And as you can see, nothing happens. This is for the simple reason that this whole effect is basically just an empty effect that reads the texture from the screen and just outputs it without changing anything. But here we can just copy paste our entire Shadertoy code into this FSH file, and also don't forget the main function. And we have to do a bunch of replacements. For example, here we see iTime, and we also see this iChannel 0. And these are both things that don't exist in Minecraft. Instead, we have to import them from different points. For example, here I have the default resource pack imported in my project, and there's this globals.gsl, and it has a game time variable. So I can just import this globals include file, and now I have game time everywhere, and I can just define iTime as being replaced with game time. And because game time goes from 0 to 1 in the span of 1,200 seconds or 20 minutes, I have to write times 1,200, and then it will be basically the same as iTime because it's both measured in seconds. And the next problem is just this iChannel 0 that doesn't exist in Minecraft. Instead I have insampler. And next, this frag chord and I resolution also doesn't exist. Instead I have text chord. And it basically does the exact same thing. So I think now everything should work when I reload my resource pack. Very well. And I have this whole effect in Minecraft. So the next thing that I want to add is these eyes in the corner. And I want the eyes to be controlled by a texture. So inside my resource pack, I have this textures/effect folder, and any texture I put inside the effect folder is something that I can use inside a shader. So I will just copy this whole path and open it inside pay.net. So I make a new file, maybe do a 400 times 200 texture and make it all transparent. Actually, I don't like 400. Maybe 3 to 4 is better. Okay. And now I can paint some eyes in the corners. Also, I'll use straight edges like this. Okay. One eye is done. Another eye. I'm not paying attention to make them look nice right now. I'm just doing anything, just in programmer art. Okay. And also mirroring them to the other edges of the screen. There you can see all the corners have those eyes. Now I can save it into the folder that I just set. Okay. And now I can specify this texture, this eyes.png, inside my effect JSON. So every pass, like this first pass is the one that calls my custom.fsh, which I just wrote my program inside. Every pass has some inputs. It's just a list of different targets, but you don't have to write these targets that you can write to. You can also write textures inside this effects folder. So the sampler name is still required, so let's call it eyes. And then I need a location. This is just, in this case, eyes.png, I think. And a width and a height. So width was 300 pixels and height was 200. Okay. Now I expect it to work like this, and I can use this this sampler that I just defined. I wrote eyes in here, so I can write eyes sampler. Okay. Now I can use this and basically abuse it for my own purposes. So let's write this texture into its own variable. So vec for eyes color equals texture of eyes sampler and text chord. And now we can combine this into our output color. So text color equals mix of text color and the eyes color.rgb, and the mixing progress is just the eyes color.a. So any pixel where this is transparent, it just takes the first value, and any pixel where it's fully opaque, it takes the second variable. And now it should work. Let's try reloading the resource pack. And it doesn't work at all. Maybe because .png wasn't actually correct. Yeah, that's right. Now I can see the eyes in the corners. But this wasn't actually the interesting part. The interesting part is having these eyes actually open and close dynamically. And for this, we can go back into the texture and basically define for every eye individually how it should open and close. So maybe all of these eyes are something that an artist already handed to you, and now you want to add your own animation to it as a shader artist. And for this, it's useful to basically abuse every single color channel that you can make use of. So for this, I will write all of the eyes that we have so far into the red channel. So let's globally select all white pixels and all black pixels, and take this selection to another layer and fill everything with red. So this is 255, 0, 0. Fill it like this. And now we can set the layer to multiply. And now all our eyes are just written into the red channel. And we can use the green and blue channels for our own data. So let's combine these layers so that the pixel color is actually written like that. And now I can select this single eye like that, and go to the other layer and add a gradient on top of it. So now instead of using red, I will use green and make sure I'm just writing to just a single channel. And when I press G, I have this gradient tool selected, and for this I can write a linear gradient. Okay, and this linear gradient basically encodes how this opening and closing progress should look like. So in the shader we can write a program that just animates maybe a variable using a sine function, and when the variable is less than a given green pixel, then this pixel is displayed as opened, and otherwise it's displayed as closed. So this gradient can then be applied to every single eye that we have on the whole image. So let me just do that. Okay, and just use additive blending to add the two different color channels together. So now when I look at this pixel, for example, you can see that it's black on the red channel and very green. And this pixel, for example, oh, I didn't combine them yet. Okay, and now this pixel, for example, is completely red but also green, so it ends up looking yellow. And in the shader we can read these channels independently. Also, I didn't do the other eyes yet, but I can just delete them and do the whole mirroring process again. So now I have it on our sides, and I can save. And well, when I load it in Minecraft, it doesn't look very pretty. But that's because I didn't edit the shader yet to only use this one channel. So I can let the color use just the R, but I can also do some cutoff, like multiply the or subtract some value from the eyes color.a. So eyes color.a minus equals the eyes color dot G, because in the green channel I wrote the opening and closing animation, and modulate this with a sine function. So maybe let's do plus sine of I time. Let's see what this looks like. Okay, I think it's a bit inverted, so let's maybe do 1 minus this value. Yeah, and now it's opening and closing from the outside to the inside, but also everything else on the screen looks very odd. And this is for the simple reason that, again, this can be less than 0 or more than 1. So let's just do min of 1 and this value, and max of 0 and this value. Oh, yeah, the result needs to be clamped between 0 and 1. So eyes color.a equals the clamped value between 0 and 1 of eyes color.a. Okay, now it makes a lot more sense. and you can see all the eyes are opening and closing. The next thing that I'd like to change is basically all these eyes are completely in sync, but I want them to have their own opening and closing cycles. And for this I'd need to distinguish which pixel belongs to which eye. Lucky for us, this whole eyes texture still has the blue color channel completely unused, so I can just select each eye and use a different blue color channel for each. So let me just do that. So here I will just set red to 0, green to 0, and set blue to 1, and use the fill bucket tool. And now it's this mostly black color, but when I later change the mode to additive, it will just add this blue value of 1 to the whole color of the eye. And I can repeat this process for all of these eyes that you see everywhere. Okay, now I have a different value for every eye. I can set the blending mode to additive, just as I said, and combine the layers and save the texture. And now I can just change this whole sign function by the eyes color dot blue and multiply it by 255, because basically this is a value between 0 and 1, and the value that I entered here is a value from 0 to 255. So now it matches what I entered, and I can write maybe some different value like 1.6. Okay, now let's reload it. And I hope we'll see all the eyes move at different phases. Yeah, we do. You can see all of them are moving completely differently. Actually, one more thing I want to show is what this looks like with the correct texture. Like, this is the actual artist texture that I didn't just make in 10 seconds. So that looks like this. And as you can see, it's a lot nicer. And well, having this better art also inspires to add a bit of a better effect. Like, for example, here on the alpha I could add a step function, like eyes color dot a equals a step of eyes color dot a, and step it at, I don't know, 0.3. Oh, I forgot a semicolon. And then it basically looks a lot more like animated pixel art. Yeah, and now you can see it already looks a lot nicer with these simple changes, and I hope this makes it quite understandable how you would add an effect like this. To demonstrate the usefulness of the techniques you learned in this video, let's try using them in a different order to create a completely new effect. First, we make a gradient that is shaped like the shape that we want to show, in this case a circle, and use the smooth step function to apply a sharp gradient. Next, we use the abs function to mirror our UV and get a second circle on the other side. We can first zoom out and then repeat our pattern infinitely by using the fract function. Next, let's sprinkle in some variation by randomly rotating our squares depending on a random number. We can give our lines a nice glow by using 1/x instead of our smooth step function. We can create some texture by using the smooth noise function that I explained earlier. The smooth noise can create a smoke effect just by adding and multiplying it to our brightness value. And we can create more detail for a noise function just by adding together multiple scaled versions of the same noise function. We can also tweak it a bit so it looks right. Let's also add the time to our UV to create a shifting animation. And after tweaking it a bit more, we get this as a final result. That I can create all these different effects using the simple toolbox that I showed in this video demonstrates the usefulness of the techniques that I showed. So I really hope that you will use this knowledge to create your own shaders and maybe join me on Discord and share them. So this was it for post effects, which run after the game has finished rendering its main image. And for the next video, I will explain core shaders, which you need to interact with the game's internal rendering. I will demonstrate this by importing complex 3D models, creating interactive minimaps, and making other fun effects. So if you're interested, subscribe so you don't miss when it comes out. Please like the video, and see you next time.